Montclair State University. Today it is my good pleasure to present our work, AuthPDB, Authentication of Probabilistic Data Queries on outsourced uncertain data. And this work is in collaboration with Dr. Boxiang, Haipei and Dr. Wang from Stevens Institute of Technology. So nowadays, we are facing a lot of uncertain data. In general, uncertain data contains noise that make it deviate from its original values. So for example, data generated from information extraction and sensor data management have noises due to the errors in the devices. So how to deal with uncertain data is becoming more and more important. Probabilistic database systems have been considered as a successful tool for managing uncertain data. Here is an example of probabilistic database, which stores the information of house renting information collected from the internet. Each tuple corresponds to a property listed online for rent. However, because some rental listing could be a scam, each tuple is associated with a probability denoting the likelihood of the probability that it exists. So, based on the database instance, we have the definition of possible word. A possible word is basically a subset of tuples with a probability. Intuitively, the number of possible words of a database is exponential to the number of records. So here I show two of the possible words from the database. The first possible word on the bottom left includes two tuples, T1 and T2, and the probability of this possible word is just P1 times P2 times 1 minus P3, since T3 does not exist in the possible word. Next, I want to introduce the definition of heat set, giving a query which returns all property records whose price is no less than $20,000. Obviously, the heat set is T2 and T3 because the price of them are larger than the 20K. So in this paper, we consider two types of queries: the all-answer query and the Topk query. All-answer queries is defined as the union of all unique results found from the possible words, while Topk query are the K answers with the highest probability. So the figure on the bottom shows the possible words and their corresponding probability. And so the all-answer query result will be A1, A2, A3, and A4, as well as their probability. But for the top two query, the answers are A3 and A2 since they have the highest probability. And here it's not too hard for us to find that the all-answer query results can be generated from the heat set, and the number of possible answers is exponential to the size of the heat set. So here, according to the literature, the evaluation of most types of query over probabilistic database is sharp P complete. So it is necessary for a data owner with a probabilistic database but limited computational power to outsource the query needs to a service provider. In this framework, the client submit queries to the server, and the server just return the query results to the client while charging the data owner based on the amount of resources that have been consumed. So, however, in the outsourcing scenario, there is a very serious security issue with the server, because an untrusted server is incentivized to improve its revenue. So it can compute the result with less resource, but charging for more. What's worse, a malicious server could just forge the probability of possible answers as a random value or just return wrong result intentionally. So we need to design an efficient and robust authentication method. So there exists some work which focuses on the query authentication on the deterministic databases. The main idea is to build an authentication data structure, or ADS in short, to generate proof for all the queries. But since they do not consider the probability of the answers, they do not work for the probabilistic databases. So in this paper, we consider the following authentication goal. For all answer query, we need to verify the authenticity to make sure that all the answers actually exist in the database. And second, we need to make sure that the returned answers satisfy the query range. And lastly, we want to verify the completeness of the result. Well, the verification goals of the Topk query are similar to the all answer query, but it has an additional goal, which is to check the Topk soundness, namely to check if the returned answers have the highest probability. So this is a brief summary of our contributions. First, we design a novel authentication data structure, and then we propose a authentication scheme for the all answer query as well as the Topk query. And so this is the outline of my presentation in the following 10 minutes. First, I'm going to introduce our authentication data structure named APB tree, and then I'm going to present the authentication schemes. Following that is the experimental results and the conclusion. So first, this is the system overview of our authentication approach. In this framework, there are three parties: the data owner and the client, as well as the server. So the data owner first needs to construct the ADS from the probabilistic database, and then he signs the ADS and the database to the server. Meanwhile, he also signs the root signature of the ADS to the client. The server will respond the client to their queries and send the results, while as well as a proof constructed from the ADS. In the last step, the client just verifies the result by using the root signature as well as the proof. So this is the brief introduction of our authentication data structure. The structure is very similar to the traditional Merkle tree, but so we add additional information in the tree structure. In particular, in the leaf nodes, we include the tuple values as well as its probability, and also a RSA signature from its tuple and probability, and also a hash value. While in the internal nodes, we include the lower and the upper bound of the values stored in the subtree, and also the aggregated probability from its leaf nodes, and also the aggregated signature from the leaf nodes, and also the hash value. So the purpose for us to include the probability and use condensed RSA and aggregated probability in the ADS is to make sure that we can verify both the tuple and answer probability just by using information from the ADS. So next, I will discuss the authentication of all answer queries. Once we have verified the hit side, a naive way to verify the all answer queries to generate all the possible answers from the hit side. However, the complexity will be too high. And so, and then we propose a method to significantly reduce the complexity. And this is based on the property that we discover from the answers of the all answer query. So, giving a pair of answers which just differed at a single tuple T1, then the division of the answer probability is just the ratio between the tuple probability and 1 minus the tuple probability. So based on this finding, and this property, we design a AP-Lattice structure. And so in this structure, each node corresponds to a possible answer, while each edge indicates the difference between the two answers. So the the answer pairs with the same edge label is going to be grouped into the same cluster. And so, for example, here we have A1 as T1, T2, T3, T4, and A2 as T2, T3, T4. The difference is T1. So if we want to verify the probability of A2, the naive way is to recalculate it from the scratch. However, based on our probability, we can calculate its probability by using the probability of A1 times 1 minus the probability of T1 divided by the probability of T1. And this is much more efficient than calculating from scratch. So now I'm going to present our authentication method for the Topk queries. So the naive method is just to distill the Topk answers from all the possible answers. But again, the complexity will be too high. So we design a method which significantly reduces the complexity of the verification for Topk-ness based on divide and conquer. And the high-level idea is that since the possible answers is related to all the heat set tuples, we either aggregate the probability of the tuple or minus 1 minus of that probability. Since we only need to get the Topk probability, we can actually prune out those probabilities that couldn't be in the Topk side. If we construct the possible answers from bottom to up, and so then we design this method based on divide and conquer. And next, I'm going to present our experimental results. So we use 2 datasets from the real-world setting, and we prepare queries whose heat size varies from 14 to 26. In this figure, we show the veil construction time. On the left-hand side, we show the so we can say that the veil construction time goes linearly with the selection ratio. While from the other 2 figures, we can say that the veil size is relatively small and is negligible compared with the query result size. So in this figure, we show the verification time. From the left figure, we can say that the verification time of all answer query increases exponentially with the heat set size. While from the other 2 figures, we can say that the verification time of Topk query grows subquadratically to the value of k, and also in general it is very fast, less than 20 milliseconds. So, and in this slide, we compare our approach with the baseline. So from both figures, we can say that our verification approach is at least 30 times more efficient than the baseline method. And also compared with local query execution, our method is at least faster by 3 orders of magnitude. So now I'm ready to conclude our presentation. So we design AuthPDB, which includes the authentication structure and also the authentication method for the all answer query, as well as the Topk query on outsourced probabilistic databases. And our experimental results demonstrate the efficiency of our approach. In the future, we want to extend our work by considering more probabilistic models and more types of queries. So thank you for your attention. Please let me know your question, and also you can reach us by the following email address.